going to look at a little bit at the binomial theorem. We want to have a use of Pascal's triangle and to use the formula. So let's have a little look now at what we've got. So this is Pascal's triangle, and you start off generating one row at a time, and it's quite easy to work our way down. So always down the sides we're going to get a 1. So these numbers here are going to be 1s. And then what we do is we take the two cells above it, add them together, and we get those values in this one. So into the next row, we're going to get a 1 here. What number should I get there?
4.
4?
4. Oh, 6. 4. 4.
What's going to get here?
1.
And the next one?
5.
And the next one?
10.
And the next one?
5. 1.
What you'll notice is that there's like a mirror image pattern in the as you go across. Yeah. Okay, so the 6th row. What are we going to get in the 6th row?
1. 6. 15. 20. 15. 6. 1.
Alright. So this is how we can generate. Pascal's triangle is incredibly interesting. We're going to use it for binomial expansions, but if you read up on this, if you're interested in a bit of math, there is so many different things you can find in this, and you tip it on its side, and then you've got the numbers here, and you do this with it, and then it generates these numbers. It's incredible how this sequence fits behind a lot of stuff. But anyway, we are going to use it for expanding expressions like this one. I'm going to skip this bit. I'm going to go to here. I'm going to go to here. I'm going to have a shorter lesson today because I'm not feeling so well. So use Pascal's triangle to find this one. Let me show you how to do it. So in this one, this is the 3rd row. This is the 3rd row. We're going to the power of 3. So here in the 3rd row, this is row 3, we're going to want these coefficients. Notice how that the number of coefficients we're getting from Pascal's triangle is always going to be 1 more than the degree. The degree was 3, you should get 4 coefficients, just so you're finding the right one. So the degree here is 3, we get 4 coefficients, so we are going to get 1, 3, 3, 1. Now, with this, we have this in the form of a plus b to the 3. So whatever we have here as our a is x, we're going to take that one, and we are going to have that one up to the full extent of the power, up to the 3. Then we take the other number, that's, in this case that's a 5, and we're going to have that one to the 0. Now as I come up to the next one, I'm going to have x to the 2. I'm going to have a 5 to the 1. Notice how that one of them goes up, the other one goes down. So the next one is going to be x to the 1, 5 to the 2. And then the last one is going to be x to the 0, 5 to the 3, 5 to the 3. So just collecting them all together, we are going to get x cubed, and here we're going to get 15x squared, and here we're going to get 25 times 3. I'm going to need help with math today. 75x, and here on the last one, 5 to the 3 is 125, and the x to the 0 is obviously.
Why is the first one 0? Because if you're multiplying by 5 to the power of 0, why don't you just get...
What is 5 to the 0?
Oh yeah, it's 1. Oh. I realize it. But
No.
We increase the
Sorry.
exponent. We increase the exponent every time for the constant. We increase it every time.
We increase the exponent every time for the b,
Yeah.
the last term in the expression, and we decrease it every time for the first term in the expression. So let's.
This is just an easier way to expand.
Yeah, particularly longer ones. So let's try this one. This one gets a little bit trickier. So in this one, what is a?
2 x. No.
What is b? negative 1. So always have it as a plus. So instead of having it as a plus, rewrite that as plus negative 1. Okay? So I'll help you put in the first couple. Let's start putting a couple in. So we need to find the coefficients. It's going to be the same coefficients again because we're in the third row. So we're going to get 1 plus 3 plus 3 plus 1. So then we need, in our black one, it's going to be 2 to the x to the power of 3. And our red one is going to be negative 1 to the 0. This one's going to be negative 1 to the 2, negative 1 to the 3, negative 1 to the 4. And then our black ones are going to be 2x to the 1.
2.
And then 2x to the 1.
2x to the 0.
2x to the 0. Okay. Try and work out the last line now for yourself.
Because 0 and 2 is the same thing as 1.
The red ones are wrong. Sorry. Look, I missed it here a little.
0, 1, 2. Yeah.
What's that? 0 to 1.
Do you know that? So long.
That's just going to toggle plus negative plus negative plus negative.
Because to the part 2 is positive. The part 1 would be negative. It's negative. Oh, it's negative.
All right, let's have a look at how this simplifies. So, negative 1 to the 0. What's that going to be?
0. That's correct. Or 1.
Anything to the 0 is 1. So we're going to get 8. We're going to get 8x cubed. Now here we have negative 1 to the 1, so this is going to give us a minus sign. This is going to be an alternating sequence. We're going to get 4 times 3, so 12x squared. Then we're going to get a plus. This is going to be 2 3s are 6. And then our last one's going to be a minus. And that's going to be minus 1. Let me pause for a second while you guys discuss that. Okay, so you can use Pascal's triangle to generate the numbers, but it will always take you a little bit of time. You probably put up the first 3 rows, rows 0 to 3, fairly quickly, but then you're going to have to use Pascal's triangle to get all the way down. If you wanted the 12th row, it's going to take a while. So we do have another technique to get these coefficients a little bit quicker using a formula. So let's have a look at that formula now. So we can get the coefficients using this formula, using NCR numbers. This is your binomial coefficients, that they're called, and we can find them a little bit quicker. Let me show you how they relate to Pascal's triangle. Let me show you how they relate to Pascal's triangle. So for instance, if I'm looking at row 3, what we've got here in row 3 is we have n is equal to 3, and this is the first term in the sequence. The first term in these sequences always starts at a 0. Notice how the rows start at a 0 as well. The reason we count from 0 to n is then you'll always have n plus 1 terms and n plus 1 rows. So a handy technique of when you want row 3 to have 4 terms is you start off with terms 0, 1, 2, 3, and then you end up with 4 terms. So we are starting off with row 3, column 0, row 3, column 1, row 3, column 2, and row 3, column 3. So we have a referencing system like this one, where we can use, I'm using a binomial coefficient, where we have n comma r as our values there. So we can write it like this. You're going to see it written like this. This is how the IB writes it, and this is how the AP writes it. And this is how the calculator writes it. Okay?
Why so many different forms?
And there's the IB right there. What is it? They're all NCR one.
That's yeah.
So I'll recognize any of these four. It's not hard to move between them. So if we wish to get a particular number, what would be, let's say we pick out this one here. What is the NCR for that? What is the value of n? What is the value of r?
10 over.
No?
5 over
5 over 0, 1, 2, 3. This is 5. So 5 over 3 is equal to 10. Let's have a go at that.
What is 10? What is the fifth row number 3 standard? What is 10?
So we want 5 over 3. Let me show you how to do this. So we've got the formula here, like this one. We are going to want 5. What does this symbol mean?
Factorial.
Factorial. This is how we say factorial. So we want 5 factorial over 3 factorial times 2 factorial. What does 5 factorial mean?
It's like 1 times 2 times 3 times 4 times 5.
Always best to start at the 5 and go down.
So it's 5 multiplied by 4?
The reason being, when you say 5 factorial, and then you say 5 times 4 times, it's much easier to remember. I don't know. I think it's harder. You say 5 factorial, then you start counting up from 1. You go 1, 2, 3, 4. What was I going to? Whereas you start with 5 and you go 5. You know exactly what you're starting from, and then you just go down until you get 1. And anyway, we are going to get 5 times 4 times 3 times 2 times 1. What about 3 factorial?
3 times 1, 3 times 3 times 3 times 2 times
2 factorial?
2 times 1.
So then what we can do is we can cancel them. So 1, 2, 3 cancels this 1, 2, 3 here. This 2 halves that 4 into a 2. We've got 5 times 2 again. 5. So this is going to give us 5 times 2, which is 10. Have a go at finding 12C10.
How did you get 2 again?
Read the formula. Read the formula.
Read the formula.
Let me pause while you chatter. Okay, so what you want to do for this one is we are going to need 12 factorial over 10 factorial times 2 factorial. This one at the top, don't pull out all the terms from 12 down. Just pull out 12 times 11. Pull out 2 terms until you get to 10 factorial. We're going to leave this one as 10 factorial, and this one's going to be 2. It's not 2 factorial, it's 2 times 1, which is 2. The reason I do that, you only need to pull out as many terms as are going to get cancelled off. It's that 10 factorial cancelling that 10 factorial. So you're left with 12 divided by 2, which is 6. So 6 times 11. 6 times 11, 66. Okay, let's have a look at the binomial theorem. So for expanding powers of binomials, we're going to get something that looks a bit like this. So here we see a formal definition of the binomial theorem, We've just seen this. This is, what I'm showing you here, is this, with the different colors, the blue, the black, and the red. Let's go back again and see where it is. So here we see the general term. This is the general term. So this first bit here is the blue bit. It was that coefficient number, the NCR. And then I had black as my next color. That's this bit here, which was simply whatever was there to the power of cascading values of n, starting with the n and then going downwards. You can see that here. Look, it says to start with n, and then use n minus 1, and then use n minus 2, until you get all the way to the end where it disappears. So the next bit was this one here, which was whatever number we've got in there, whatever number expression we've got in there, increasing integer value, starting at 0, going up. We start at 0 until we get all the way up to n. You can see it going up here. Here it's at 1, here it's at 2. So when you show a sequence like this one, it's normal to show the first 2 or maybe 3 terms in the sequence, so we see how the progression works. To see the last term in the sequence, how it's going to get to. This symbol here is called the ellipsis. And it says it can continue and expand at this particular point. So we can see here that it's expanding either side of that. So what we've basically got here is our general term. And notice how all of these are added up. We add them all up, don't we? So all you need to do is you can express it like this. And this is the general term. We've got 3 bits. We've got the bit I had in red, the bit I had in black, the bit I had in blue. And this symbol is a way of expressing this much more concisely. The capital sigma means it's a summation formula. We are going to sum this formula from all of the numbers where r starts being 0 until r becomes n. So we're going to go from r equals 0 up until r equals n.
What if r is like negative?
It says r starts at 0.
No, but like, would there be another way to do that? Or is that just what we're doing? Is it like all 0? Like, is it positive thing?
In the binomial theorem?
Yeah.
Yes, because we're counting. We're counting up to n. We want n plus 1 terms. So we go from 0 to n. And r counts from n down to 0 or 0 up to n, whichever way we want. You can make a summation symbol, include negatives and things, but usually when you're summing a term or a sequence, you start at 0 or 1 and go up to n, depending on whether you want n number of terms or n plus 1 number of terms. So all we see here is a very compact way of writing all of that. So here we can see a very compact way of expanding that, and this is how we write it. So we're going to learn to use that one a little bit now. So we want, and I could write it as so x plus negative 1 to the 8 is what we're after this time. We want the 4th term in the sequence. So what's the general term? The general term in this is NCR, a to the n minus r. So we want NCR, we want x to the n minus r, we want negative 1 to the r. So just taking the general formula here, sticking it in with these numbers, we want this. So how do we solve the problem now? Well, we want the 4th term in the expansion. So this means that r is going to be, is r going to be 3 or 4?
3.
Why?
Because we start at 0.
So r is going to be, to get the fourth term in the sequence, we want r equal to 3, because we always start counting from the first term in the sequence is 0. The second term in the sequence, r is 1, we always start counting at 0. So for the fourth term in the sequence, we are going to need 8c3 x to the 8 minus 3 negative 1 to the 3. This will give us the fourth term in the expanded form. Have a go at finding this value now for yourself. Okay, so first up we need to find our 8c3. So we need 8 factorial over 3 factorial times 5 factorial. So expanding the top, we have to take out 8, 7, 6, and then we'll stop at 5 factorial. Here we need 3 times 2, and then we need 5 factorial. Our 5 factorial will cancel out. 2 times 3 is 6. So 8 times 7 is 56. 8 times 7, 8 times 7 and 7 times 6 and 6 times 8, those are the 3 hardest multiplications in the multiplication table. For some reason, those are the ones that everybody struggles with. So 9 is easy. Because we always add together. So we are going to need minus 56 x to the 5.
Yes, I got it. Also, it's 8 minus 3 is 5. Why is that? And then you multiply by 1. If you do the root, you multiply by negative 1. That's why I made a negative 4.
Alright, can we... Do we have any questions before we go? Yes.
How did you go from that, the black, to the first thing? Oh no, because n is 8, n is the degree, or is the...
So, I'm using the formula here,
8 minus 3.
Yeah.
and I've decided that the fourth term means that r equals 3. Because we go 0, r starts at 0, 0, 1, 2, 3. So the fourth term, r equals 3. Alright, have a go at one for yourself.
Yeah, I can just always extend. So I'm going to go 0 to 5. 2x times 9 and 5. Factorial is 9 and 5. So it's 9 or 5.
Okay, so I'm going to use my calculator for this one. We want the 6th term in the sequence, so what is the value of r?
5.
R is going to be 5, so we need 9c5. We need 2 to the x to the n minus 5. What's n minus 5? 4. And then we need negative 1 to the 5. So let's find 9c5. I said we could use the calculator, so take your calculator in your hand. I'll show you how to do this one. What we're going to do is we can put it into the calculator. So binomial coefficients are from the probability section. This is the number of correct combinations. So we get the probability and combinations. That's what C stands for. It stands for combinations. So we pull up this and we type in 9, 5, and it tells us the answer, 126. So we're going to need 126 multiplied by 2 to the power of 4 times x to the 4 times, well, minus 1 to the 5. If this is an odd exponent, it's just going to come out as 1. If it's a negative 1, if it's an even exponent, it comes out as 1. So let's just put that into the calculator. 2 to the power of 4 is 16. Multiply that by 126, and we get negative equals negative 2016. X to the 4.
What did you press on your calculator?
Menu, probability,
Probability.
and then C for combination.
Combination.
Then you put in N comma R. The comma is found down here. See on your N comma R, that was 9 comma, what was it?
9.5.
4, 5, 5, 9 comma 5.
How?
Okay.
That's what I got.
Can I have quiet on this one? This one's going to be a little bit trickier. I'm going to explain binomial probabilities now. We have this question. So we're going to start off by saying that it says here in the question, X is the number of, what does it say, correct answers. We just define that at the beginning. We've got a multiple choice quiz. What is the probability of success in getting 1 right?
1 to 4.
So the probability of success, I'll call that lowercase p. And that's going to be 1 out of 4. N is our number of trials. And how many times do we try? 6. We tried 6 times. We tried 6 times. So I'm going to show you 2 ways to do it. I'm going to show you how to do it on the calculator. I'm going to show you the theory behind it a little bit. So let's start thinking through. It's going to take me a bit of space, this one. Let's start thinking through the probabilities. So we need to get 2 correct. So what would the probability be? Let's have our first stab at it. We need to get. So this is us getting. This is us getting 1 correct.
So 116.
This is us getting 1 correct. How do we get 2 correct? What do we times by?
1/4.
We do 1/4 times 1/4. Let me generalize it like that. This will help us. So that means I've got 2 of them right. What happens to be the problem? What do I have to do to the other questions to answer the question that we're after? What do I have to do with the other 4 questions?
You have to put.
What's the problem? Do I have to get them right or wrong?
Wrong.
To get, if we read the question, to get the probability of getting 2 correct means I get 2 correct and 4 incorrect. What's the probability of getting a question incorrect?
3/4.
Yeah, 4s. So this is going to be 3 over 4. How many times do I have to be wrong?
4.
Okay. Is this the probability that we're after, getting 2 correct and 4 wrong?
Yeah, but this is only for 1 test, not 6 tries. You have to do this.
No, I keep going. I don't think you're quite right, but at least you're going in the...
I'm saying like this is for 1 test, right?
Yeah?
So there's 6 tries.
There are 6 questions.
Questions.
That's why 2 plus 4 is 6. Is this the correct probability? Not quite. It's not quite. Let's say we get the first ones correct, the first 2 correct, and then we get the next 4 wrong. I'm even going to use true and false. True and false. And I'm going to do a little table to show you how. So I could get the first two correct, and then the next one's wrong. But I could get the first one correct and the second one wrong. Can I still end up getting two right?
Yeah.
I could get this one correct, couldn't I? But there's other combinations, isn't there? I could get the first one correct, the second two wrong, and then the fourth one right. I could get this one correct. I could get these two. And then I could get this one correct. I could get all of these wrong. And I could get this one right. Is that all of them?
No. Because the first thing you mean.
So this is, we have 5 ways of getting the first one right and then the one other one. So we have to get the first one wrong now. So we could get the second two correct. Like this. This technique that I'm using here is a good problem-solving technique because I'm being very strategical on how I move across. I'm not just randomly picking numbers. Notice I'm keeping this one locked in place, and then I'm moving this one across one at a time. So now I'm keeping this one locked in place, and I'm going to move this one across one at a time. Count them out. Because this one now always has to be false. So this one has to be true. This one's going to be false, true, false, false. False, true, false, false, true. False, true, false, 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 true. So, how many were there here? Here there's 5. How many are here? Why is there one less?
Because the one that's already.
So we'll get less and less each time. This time I'm going to start off by getting the first 2 wrong and this one right. And then I need to have one more correct.
That's 3.
And then we want this one. And then we want this one.
Yes, no.
So that would be.
Then we want.
So this would be our 5 factorial.
Not quite. Sorry, what am I doing?
That one's true.
That one's true. This one's false. And then we want false, 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 true, false, true.
You see, right?
And then the last.
False, 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 false. Last 2 true.
I don't know why.
What's the total?
5 factorial.
5 plus 4 plus 3 plus, we're not timing, we're adding, we're counting. How many different combinations are there? 15. 15.
So do you have to do this?
That would have to do every
You
part.
understand?
Alright. So if we look at this number, we've got a coefficient number at the beginning. We've got, notice that this and this add up to give 6, the number n, the number of trials. N is 6. 2 and 4 add up together give 6. We want x to equal 2. So this is n minus 2. This is that number n minus that number. Can you see that this looks a lot like a binomial probability?
Yeah.
And in fact, if we go back to Pascal's triangle, isn't 15 in Pascal's triangle?
Yeah. Row.
Where's the
Row 6. X It's number 2 and number 4.
So this 6 and the 2, the 6 and the 2, where's that coming from in our question?
I don't know. 6 is and
The question is how many correct?
We want x equal to 2, and we've got n equal to 6. 6 and 2. Okay, so we can do this. There is actually a really short way of doing it. We want the probability that x equals 2. What is x?
Number of questions correct.
yeah.
Number of correct answers.
The number of correct answers. So we want to calculate this. All we have to do is we have to explain this information here at the top in terms of math. So the way that we do it is we create a binomial model. And our binomial model, we say that x is the number of correct answers, where x is distributed binomially. So this symbol here means it's distributed. The b means binomially. And then we enter in the number of trials. There are 6 trials, and our probability of success is 1 over 4. So the mathematics for all of this is simply this bit here. We say that x is the number of correct answers, where x is binomially distributed, with 6 trials and a probability of success of 1/4. What is the probability that x equals 2? And then we say calculator. Tell us the answer to this. Sorry. Shh. So, we're going to press menu, probability, distribution. It's a binomial distribution. So, we want a binomial PDF for this one. How many trials?
6.
What's the probability of success?
2.
No.
1 over 4.
1 over 4. What do we want x to equal?
2.
I cannot do this. Wait, they're not correct.
So we get 0.297. Now, wait a second, we have to do the magic. What was this? We never calculated it. Let's try it now. So the manual version was 15 times, I'm just going to put it in as we see it, 1 over 4 squared times 3 over 4 to the 4th.
If I multiply by 15, I would have got it right. I'll just go ahead and divide it to the track and give it a go. The same way. The track.
We have to put it as 50 or something.
Wait,
So we see here, we get the same value as with the binomial distribution.
Yes.
Sir, can I take a picture of this?
Everybody saw this actual answer.
Sir?
Okay, that is it from me today. I'm going to finish there at that point.
I was